Welcome. Hold on. Oh, Federico. Sarah, have you started recording, by the way?
Yes.
Okay, that's great. Good afternoon, everyone. Welcome to the HAO colloquium. And today we are very glad to have Professor Scott England from Virginia Tech to give a talk. And let me start with a brief introduction of Professor England. So Scott is associate professor in the Aerospace and Ocean Engineering AOE department at Virginia Tech. He did his PhD at the University of Leicester in the United Kingdom, studying coupling of energy and momentum between different regions of the atmosphere via atmospheric waves. And he spent 12 years at the Space Science Laboratory at the University of California, Berkeley, where his studies focused on the interaction between atmospheric waves and charged particles in the near-Earth space environment. He has been working at Virginia Tech since 2016, where I was also there, and currently focuses on using remote sensing instruments to study the upper atmosphere and the near-Earth space environment. And he is a project scientist for the NASA's ICON spacecraft and a co-eye on the NASA's Gold mission. And today he's going to talk about watching the thermosphere respond to disturbances, tracking large-scale thermospheric gravity waves with Gold. So please take it away, Scott.
All right. Thanks, Tom. Thanks, everyone, for letting me present. So I want to talk about gravity waves. We're specifically going to look at them in the thermosphere. We know gravity waves are in all levels of Earth's atmosphere. Whenever we get a disturbance to the background atmosphere that has the right kind of spatial scale of maybe a few kilometers or so, temporal scale of a few minutes to a few hours, you can generate these waves that then will propagate away from that disturbance. And when we see in the thermosphere, we're going to see traces maybe of waves, some of them coming up from below, some of them may be generated in thermospheric altitudes. And really, we're going to focus on observations with Gold, but I'm going to bring in some other data sets here. I'll make use of some ground-based TEC observations, which Shenron Zhang helped to provide, and also some wind observations from ICON, and pull those together into an analysis so we can get a better picture of these waves. Very quick outline. I'll go through some of the observations, some of the things we've seen with gravity waves and then their counterpart TIDs, and then zoom in on the region we're going to look at. So we'll be looking at waves in the middle thermosphere. We'll talk about the Gold instrument, how it takes data, the campaigns to get the gravity wave observations, how we then use those to do an analysis and extract the wave properties, and then rounding it out with leveraging these other data sets to sort of fill in some of the other context information and provide a couple of the missing parameters. So, if we look right sort of at the base of the thermosphere, we can see waves that are coming up from low levels in the atmosphere, coming through the mesopause region. The mesopause is great because there are these narrow air glow layers, mostly OH and O2. And with an all-sky camera, you can get the 2D structure and see these wonderful wave-like perturbations of the waves coming up through that region. As you go to higher altitudes and you get into the thermosphere, it has been generally harder to get as many neutral atmosphere observations. We can still see the signs of the gravity waves, mostly in how they perturb the ions, because electron density and ions are easier to observe remotely. So the figure on the left here is showing perturbations to electron density measured with the Arecibo ISR while that was operational. And you can see these wonderful perturbations versus height above that radar as a function of time. As you get quite a bit higher and you get up to F region altitudes, then you can also get these 2D pictures of small to medium scale. Again, these are perturbations in the ions that we can see in things like ground-based TEC. And here's one where there's a counterpart with some all-sky images looking at red line. And seeing these TIDs, these ionospheric perturbations that are generated by the gravity waves, or some other instabilities. We can also see at very, very large scale signatures of these waves. So if we have an intense input of energy, typically at the high latitudes, we can get a combination of Joule heating, putting energy in, ion drag, moving the neutrals, and generate very large scale gravity waves that maybe propagate, away from the polar regions predominantly. Here's an example of a very large scale one, seen again in ground-based TEC observations. And on the right-hand side, this is a different event, but where they've taken a slice and seen how tech varies with time, both in the observations on the top and then reproducing it in a model result and seeing these waves moving in the latitudinal direction. And that sort of brings me to this cartoon, I'll say, of this is my very, very, very high level summary of sort of the observations we have with gravity waves. So we have some number of observations of them in the middle atmosphere coming from a variety of sources, including seeing horizontal structure where they perturb clouds, all those air glow layers, which let you see at nighttime the structures near the mesopause. We can get vertical profiles, maybe with a LiDAR or limb sounding spacecraft can get you vertical profiles of winds, temperatures, and we can see some of these waves there. So we know some of what's coming up into the thermosphere. As we get to higher altitudes, we've got a lot of these electron density measurements, a few neutral measurements, but comparatively few. And then up in the F region, we can get some horizontal patterns with ground-based distributed arrays of all-sky images, TEC, and the radars can give us vertical profiles from which we can see these wave perturbations. But one of the regions where there's comparatively very few observations is in that region in the middle, let's say between 120 kilometers up to maybe 200 kilometers, where there's comparatively less observations of the especially of the neutrals. And this region I would refer to as the middle thermosphere. So I might break the thermosphere up into lower thermosphere that's down near the mesopause. It's relatively cold, relatively dense. Upper thermosphere shown in green, the temperature's high, temperature doesn't change much with altitude. And then the middle thermosphere being the bit shown in yellow, where the temperature is rising and the density is falling. And that falling density in combination with absorbing solar radiation is part of what's allowing us to reach these higher and higher temperatures in that region. If we look at the this figure here in the top right, we can see what wavelengths of sunlight are being deposited at these altitudes, and there's some far ultraviolet that's being deposited here, and also a bunch of extreme ultraviolet wavelengths. And these shorter wavelengths, especially the extreme ultraviolet, they don't just heat the nitrogen and oxygen atoms and molecules that are present, right? They will ionize these because their wavelengths are below the ionization thresholds for these species. So within this region, as solar photons come in and are stopped, we're producing ions and electrons, and these electrons that get produced, these photoelectrons, can carry lots of excess energy, and they play an important role in producing the far UV air glow that we need. So at these altitudes in this middle thermosphere or so, we're producing these photoelectrons. They have extra kinetic energy. When they go and bump into a nitrogen molecule or an oxygen atom, they'll knock those into an excited state, and they can de-excite by releasing a photon in the far UV. We'll talk a lot about the oxygen 1356 and the nitrogen LBH.
Hey, sorry for interrupting. I have a question about last slide.
Absolutely.
Yeah, on this plot, yeah, on the left you had the thermopause. Could you remind me what's your definition of the thermopause there? Maybe it's that's cross plot.
It's not necessarily a definition I would use. This is me borrowing a figure from a textbook.
Okay. Yeah, never mind. I will look into the paper.
Okay, so we have this process that's emitting photons in the far UV, and a really handy thing about the far UV is these photons that are produced at these altitudes. If they go upwards, they'll go out into space. We can view them with an instrument on a spacecraft. These wavelengths don't pass through lower regions of the atmosphere, so below about 120 kilometers, they're completely absorbed, which means if we look down and we're looking at these wavelengths, the only things we're seeing is the thermosphere and upwards. There's no signature coming from reflected light off the ground or city lights or anything like this. And so that sort of leads to how the GOLD instrument is set up. So it's designed to look at these wavelengths that encompass the LBH band and the oxygen 1356. Look down at the Earth from geostationary orbit. This is a view of what GOLD sees. It is roughly over the mouth of the Amazon River. So it always sees, the Americas, the Atlantic, and a bit of the coast of Africa. At any instant in time, GOLD is making measurements along a slit that's sort of shown with this white line here. And on the detector, it's then getting wavelength versus, and this is essentially latitude along the slit. Within this are these features from oxygen and nitrogen that we're looking for. And the way GOLD builds up disk images that we're going to use here is by moving this slit. Perhaps you can see it in the movie. So the slit moves from right to left across the north and right to left across the south. And over that time, we've then got these wavelengths at all these positions in the north and south. We can combine them and make these disk maps. This is a particular one from O2N2 that I put together. So we get three distinct products out of this. We see the brightness of these features versus wavelengths, so especially the oxygen and nitrogen that we are looking for. Taking the ratio of those brightnesses and information of the geometry and stuff, we can get the thermospheric composition, this column O2N2. And then purely from the nitrogen bands, looking at the shape of this structure, we can get the temperature of the nitrogen molecules. So it lets us assess the thermospheric temperature. And you can imagine that a gravity wave moving through this region can perturb all of these. So as it perturbs the density and the composition, we'll see changes in the brightness, we'll see changes in the derived O2N2 ratio, and we can see changes in the temperature of the atmosphere. So GOLD wasn't designed from day one to look for gravity waves. It went for a couple of science targets, including tides, the nighttime ionosphere, plasma bubbles, things like that. But we knew we wanted to try to see gravity waves. So before launch, we were doing some modeling work, simulating the LBH and the 1356 emissions. These are seen on GOLD's field of view on a log scale, and you can see these have typical brightnesses of around about 1,000 Rayleighs. And they are coming from this region. This shows the contribution function. So this range of altitudes over which the emission is occurring, and you're seeing those photons. And then into that model atmosphere and simulation of the air glow, we applied what we thought might be a typical gravity wave perturbation. So we gave it some structure versus altitude, made it move, perturbed. This is just showing the temperature perturbation, but there's a density perturbation, etc., that goes with this. and then modeled the change in the radiance of the two wavelength bands that you would see if this wave was present. And you can see that the expectations before launch were for really pretty modest fluctuations in the brightness. So these are changes of 1 or 2 Rayleighs on a background of about 1,000. So it was pretty evident that in the normal mode, as this instrument is scanning the north and the south and moving by, it wouldn't have the sensitivity to see fluctuations as small as this and waves of this amplitude. You know, if a very large wave came through, maybe we'd see it, but not perhaps what's there on a more typical day. So we devised some plan to sort of get around this, which was to take one of the channels and take that slit as it's moving and simply park it in one position. So that's sort of what's shown here in this panel, where we've taken channel B and put the slit here and leave it there for the whole daytime. And what this has done is we've sacrificed the longitudinal information, right? We're not scanning it left and right, we're leaving it still. But we've increased the signal within the region where it is by about a factor of 100. So signal to noise of about a factor of 10 increase. And we can sort of think of this now as like a whole meridional chain of ground stations, as it were, that can measure the brightness, the composition, and the temperature along that slit position. And here's what we see when we do that. So if we look at one particular wavelength, like 1356, along the slit and versus time throughout one of these experiments, we see something like this. Brightness is going to maybe 1,000 Rayleighs, as you may anticipate. We see a slow change in brightness that varies with latitude and time, and this is a combination of the changing solar zenith angle and also the viewing geometry, so the path length through the atmosphere changing. You'll also see this as a small region in this instance where the detector's performance is a little less down here at about 6 degrees north, and we'll occasionally see this appear as an artifact in some of the analysis. But this smooth variation is pretty easy to characterize, and we can characterize and remove it with a simple third-order polynomial. And once we do that, we end up with these figures on the right. So each one of these is seeing as latitude versus time, and we're seeing the change here in the oxygen, here in the difference between the oxygen and the nitrogen, composition, the temperature. And you can see these are not totally smooth. There are features in here. So I hope this comes through okay over Google Meet. But you can see some feature here that's moving southwards with time, perhaps another one there. And you see it here also in the temperatures, which is an independent measure from the oxygen brightness. So what this looks like is some feature moving southwards with time, as we'll get into a bit later. From this alone, right, we've got some things moving southwards, but is it moving directly southwards or a little southwest or a little south and east? We can't tell from this one view alone. But if we can leverage some other observations, this is the ground-based TEC, where you might make out some of the same features in this snapshot. It gives us another way of seeing, if we see the same patterns in the ions, that's going to give us a way of solving this problem a little later. So at a high level, what we're going to do is the following. We take the data, we do that smooth detrending with just a third order polynomial at each latitude. Then we look and we see, the waves present in this latitude range, in this UT range. And if they are, we'll then employ a method I'll show in a slide or two to find the phase velocity parallel to the slit, the wave period, the wave amplitude are pretty easy to see. We'll compare what Boulder is seeing to the ground-based differential tech. If they see the same wave, which they don't always, but if they do, then we can use the TEC at other longitudes and tell us, is this thing moving southeast, southwest, due south, north, whatever the azimuth of the wave propagation is. And that lets us get the real components of the real horizontal wavelength of the wave. And then finally, we don't always want to work in coordinates that are referenced to the ground. You know, if we look at the wave in the background flows reference frame, so if we have the winds, in this case we'll get from icon, then we can get to the intrinsic properties of the wave, which lets us get other things such as the energy and momentum flux. So using the gold data alone, this is how we identify the apparent phase velocity along the slit. So this is a simulation where I put in some wave with slightly curved wave fronts. In this instance, you can tell it's moving south. And then we take the top latitude, we hold constant, and all the latitudes further south, we shift them forwards and backwards in time. That would correspond to propagating either south or north through this field. For each one of these, we then collapse this into a 1D, one-dimensional line, and we basically measure the area under the curve. And what you'll see here is as these wavelengths become quite vertical, I'll try and pause the movie right. I'll try and pause the movie at the right spot. If I can do that, I'm not going to be able to do that. I'm sorry. When they're vertical, this measure of the area under the curve maximizes.
You may click on the bottom left, that play button, if you want to pause. But that's fine.
I'm trying that, and it doesn't. It okay. Pauses many seconds after I click. It's completely fine. Okay. This is it actually applying to some gold data, and this movie is going very fast. I apologize. Okay, so I didn't want to show you a perfect example. I wanted to show you a noisy example and show this still sort of working. So here is the input data. You can see some features moving southwards with time here, here, here. You can see an artifact in the data just under 20 degrees, 25 degrees north in this instance. Moving on the right-hand side shows all of those angles that we shift it for, and you'll see a point where these features are sort of lining up in the vertical, and at that angle we get this peak here, and that's showing us that we have something moving southwards, and we can read off the degrees per hour that it's moving. At that instant in time, over here are the line plots that we get for temperature in red and composition in green. This is a noisy example, but you can see some features in here. You can see perhaps some small phase difference in these, which is what you would expect for a southward moving wave through this region. And with this kind of information, we can get amplitudes and periods pretty easily as well. Okay, so to really get the azimuth, we need to leverage ground-based TEC observations. Pulled in a couple of examples here. So the left set of panels is one event, the right set of panels is another event. And in this one on the left, you can see some perturbations here moving southwards in the brightness, the temperature. Maybe you can make them out in the composition here. And in the differential TEC, you can see some features going at the same angular rate. There is a slight gap. The TEC data, this is a region where we're a little bit out of the ocean, so there's less data availability. But this is a visual example of where this feature is sort of lining up with this, is lining up with this. On the right-hand side, here's another one where there's some very clear wave structures in the brightness data, the composition data, the temperatures, and it's really hard to see something in the F region TEC. There's a couple of reasons this might be. One is difference in altitude. Another is that obviously the ionosphere is perturbed by more than just what the neutrals are doing locally, right? There is a conjugate hemisphere and there is electrodynamics going on. So it's not necessarily that every time we get a wave in the neutrals, we'll see the exact same thing in the ions a little higher up. So I wanted to show an example of where this does work and doesn't work. Showing it in this format too, these are the angular rates. Again, this is showing one where these things line up and things don't. So left-hand set of panels, this is the peak we're looking for, an angular rate in composition, temperature, brightness. And here it is in the ground-based TEC. So we have some confidence that we're tracking the same feature. Here's an example of, really clear one in the neutrals, and there's just nothing there in the ions for this time, for this wave, this location.
Scott.
Yes.
Question. So do you know the kind of maybe we can call it a kernel depth for integrating the TEC versus integrating, say, the gold temperature? Or are they similar or different?
They're different, right? The TECs, this is ground-based TEC, so this is everything below GPS altitude, but it's going to be heavily weighted to the F region.
Right.
Whereas the gold T-disk and O2N2 is heavily weighted to the upper E region.
Upper E region, I see.
Yeah, so they are separated in altitude. So again, I don't always expect these to line up. I guess what I'm trying to show here is that if these all work, I can use the TEC to tell me the direction the wave is propagating in. If they don't, then this can't be one that I find the direction for. Yeah.
Next.
So how we find the direction? Well, we have ground-based TEC at different longitudes. So if we go pull out a few adjacent longitudes, we can use the timing at which we see the wave arrive at a particular latitude and say, is it arriving at this longitude first, then this, and that tells us it's moving south and west or north and east. And that gives us the azimuth of the direction of the wave. So with this so far, right, we can see if the waves are present, we can pull out their amplitudes, we can pull out some wavelengths. If we can get the azimuth, we can pull out the true wavelength. If we also leverage the icon winds, which I'll show in a minute or two, we can get the intrinsic phase speed and such for the wave. We can explore the relationship between the TIDs that we're seeing, which are F region, and the upper E region gravity waves, and then get to energy, momentum flux and stuff. So with all that introduction behind us, here's all the campaigns I'm going to look at. And I'm limiting myself to 2019 to 2022 because then I have some icon wins. The campaigns that were run are shown here in the top panel. Many of them were run in the northern hemisphere. There are some run in the southern hemisphere. A couple of things of note. They're run at different locations. This plot on the bottom shows all the locations the slit was put in for each of these campaigns. All of these turned out to be quiet conditions. F10 ranges a bit, especially towards the later ones in 2022. So F10 did get up to about 150 or so, but most of them are for low F10. Most of them are very low KP. There's only 3 of these campaigns where KP went to above 3. And for many of them, it's between 1 and 2. KP was extremely quiet, and we just, within this date range, we don't have an active period where we're running these campaigns. So this is a data set that shows us really quiet time conditions and what gravity waves are present. Final thing I'll point out, we'll come back to later, there's a period here in July of 21, where we actually have a whole bunch of days back to back, and we'll use that to zero in on one time period a little later. Okay, so we take all those campaigns, look initially just at all the waves that we saw, and pull out all the amplitudes and just take a quick look at those. So these are different visualizations of the amplitude that we're seeing in the temperatures versus the composition, or the radiance versus the temperature, composition versus radiance, and then the differential TEC versus the temperature. These are noisy, but there's some pretty clear correlation in the amplitudes we're seeing, for example, here between the brightness that gold sees and the shape of the LBH, the temperatures. Not surprisingly, a pretty good correlation, relatively speaking, between the composition and the radiance, where the radiances are used as one of the main inputs to that composition. When we look simply at all of them and try and look for a correspondence between the amplitude of the signals we're seeing in the TEC and what we're seeing with gold, we get very poor results, which is maybe expected. You know, these are at slightly different altitudes, and there is more going into the perturbation in the ions. But it shows that at least the basic amplitude of the signal we're seeing in the neutrals and the ions don't correlate very well. Moving forwards, we can pull out other factors in this, so we can see the range of wave periods we're able to see, and wavelengths. And here, these are true wavelengths, so I'm including only the ones for which I have the wave azimuth. You might expect these two to show some relationship, and they do. The periods kind of span the whole range of what we can see with gold, so from about the shortest wave periods we can pick up out to about the longest, given the length of the campaigns. Some of the directionality we can see here. So this is the phase speed shown in the zonal direction and the meridional direction. And this is showing the waves we're able to pick up. And what we can see is that what we are seeing with gold is mostly waves that are going generally meridionally. We really are not picking up waves going primarily in the zonal direction. Whether or not that is because of the instrument and the geometry of the observation, or if that is really a sampling of all of the waves in the thermosphere, I'm not totally sure. And this is breaking up between the ones in the north and south. This is breaking it up between the seasons where we have the observations. Finally, plugging in the wind. So if we know the background wind through which this wave is propagating, we can get its intrinsic phase speed, frequency, and a whole bunch of other properties for the waves. So given that we have these averaging kernels for the gold, for the FUV across the middle thermosphere, we can see that, during daytime when we're making these gold observations, ICON has winds throughout this whole altitude range. So at least for the northern hemisphere campaigns, down to about -10 degrees latitude, ICON is able to see the winds, and here I've broken them up for a particular season at a few different altitudes, looking at the zonal and meridional winds. So for each one of these campaigns, I look at the ICON winds, weight them by this kernel, and find the average zonal meridional wind through which this wave is propagating. And that lets me get to the intrinsic properties of the wave, from which I can compute other stuff like energy flux and momentum flux. And here I'm just plotting the energy flux in units of milliwatts per meter squared against, in this instance, the wave period and the wave length. These are the latitude ranges over which they are seen. So to put some, I mean, these are numbers to put some context on this, right? About 3 milliwatts per meter squared ish is roughly the solar EUV input to the whole thermosphere. Some fraction of that's what's being absorbed in this region that gold is seeing. We're hitting values of energy flux indeed. These waves are bringing of maybe 5 or so % of that. Flipping this around, looking at momentum flux, we see a result that maybe we expect that the small scale waves carry more of the momentum flux than the larger scale. I think it's a result you might expect. It's worth asking the question, are we getting the amplitudes right? And there's a couple of things going into this, but really one of the things is this this averaging kernel, right, where we have a range of altitudes over which the emission is coming from, and these waves don't have simple, infinite vertical wavelength. So we're slightly averaging out the signal. So for one of the wave cases, what we've done is gone back to that airglow modeling and rerun it. So given the signature that we saw in the airglow perturbations with gold, we've tweaked the temperature and density perturbations in the model until they match. And then asked ourselves, well, what amplitude did gold report for this wave? And it reported about 13 Kelvin amplitude. The model that provides the best fit to the brightnesses had perturbations between about 12 and 36 Kelvin within the region, within the altitude range of interest. That varies with height, and obviously we're averaging across some different points in the phase. So it may be that the amplitudes we're seeing are actually a little lower than the true wave amplitude, and maybe some of these energy fluxes and momentum fluxes are slight underestimates, maybe by a factor of 2, but it's hard to quantify without another data set. Final thing I'd like to do is go and zoom in on this time period we had in July 2021, which I pointed out earlier. So during this time period, we performed these gravity wave campaigns on several days, not quite back to back. There's one here where we were testing things out, and then we applied it for several subsequent days. So here the slit is in the same place. Every one of these campaigns runs for the same hours. And this is the same season, same year, same roughly 10-day period. So we've, as best we can, removed all of the other variables that are going on. And within this, on all of these days, except on all these days, I'm sorry, we see waves in the same latitude range. So here what I've done is looked at the amplitude of the waves that we see and compared it to what's going on these days. And here I'm using, this is a Supermag auroral electrojet index, the SME index. And I'm looking at the SME value during the time we're seeing the wave and for 6 hours prior, with the hypothesis that maybe some of these waves are coming from energy and momentum inputs in the auroral region and propagating southwards through the field of view that we had. And in this plot here, this is the amplitude of the waves in temperature versus the max value of SME during that time. And I see a trend here. I don't have a lot of data points, but it looks like we're seeing the higher amplitude perturbations when we've got the higher amplitude activity in the auroral zone. It's not clear here in the O2N2 amplitude. I don't have a quick explanation as to why it would show up in one and not the other. But at least for this small date range, when everything else is constant, it looks indicative of these waves perhaps being, many of them perhaps coming from an auroral source. By no means all, but maybe. So pulling all that together and pulling out some summary points. Gold sees gravity waves and can get their properties. I didn't go into this next bullet point in depth here, but there's 34 campaigns in this that I looked at. We see waves in 33 of them. So almost all these are extremely quiet days, and we see waves all the time. We can characterize them in perturbations to the air glow, the composition, the temperature. They get some phase offsets that you might expect for internal waves. Most, but not all, we can see the TID in the differential tech, and that lets us get the azimuth. We see a range of periods, range of phase speeds. I guess I didn't dwell on this on the plots, but the phase speeds we see go up to quite fast speeds. These are waves that must have been generated at thermospheric altitudes, be they either secondary, tertiary waves, or from an auroral source. But 600 meters per second, you can't generate a gravity wave going that fast in the lower atmosphere. We just talked about the July stuff, and then I limited this study to just 2019 to 2022 when we had icon winds. Hopefully, dynamic emission will give us winds in the thermosphere. That's a key piece that we need for this kind of study. And also, GDC has as one of its main investigations to look at gravity waves, or TADs, and corresponding TIDs in the F region, which will bring multi-spacecraft view of these and give us another really good insight into the relationship of the neutrals and the ions. That's it.
Great. Thank you, Scott. Yeah, people are also plugging online. Question time? People online? I have one. Oh, okay, Astrid.
Oh, you can go ahead.
I'll let you first. Ladies first.
So your was a great talk, Scott. Your fourth bullet, did you look further into the cases where you didn't see a TID? And I mean, is there something systematic about these ones?
I didn't see it, but there aren't. I don't have a huge sample size. So sometimes it's very clear. It's simply that we're observing the wave, and gold slit is, without spending too much time jumping around, right? There are some of these campaigns where a lot of the observations are way out over the ocean. Mm-hmm. And looking at the closest point where we've got ground-based TEC, we don't see something that relates. Maybe you don't expect that. There are other times where I've got really good ground-based coverage and things don't line up, but I didn't have enough of that latter case to really tell for sure what's going on.
Okay.
If I had enough, maybe there is some seasonality to this or something. But I've got many variables here, right? I've got Northern Hemisphere, Southern Hemisphere, East, over the Americas, over Europe.
Yeah.
And different seasons. So yeah.
Yeah. Thanks, Scott.
Give me 100 more of these campaigns, I can answer your question.
Okay, thank you, Astrid. So yeah, I have a question. I found the results on earlier slide where you showed the wave period and the wavelength distribution are very interesting. Yes, here, yeah, maybe it's just because, well, most likely because I'm too ignorant about this background. But the just compare the red and the blue, the northern summer and equinox. So it looks like during the solstice you have more the small scale, just short wavelengths, and but you don't see like short waves during the equinox. Is that just because of the sampling limitation, or?
Yeah, it's hard. I mean, I'm not sure, but I did see that trend. You're meaning this, basically this panel right here, and really the the separation.
Yeah.
It could be real. That the other thing to examine in all of this is that during the different seasons, the whole slit is illuminated differently. Perhaps I can jump back to this. So in this slide, you can see a little bit. You can see this white area here in the corner, right, or here, where there's just no data. And this is
Sorry,
because
are you moving the cursor around? I didn't
I'm
see
sorry. Okay. If you look at any of the panels,
yeah,
at the higher northern latitudes, right, there's some missing data at the earlier UTs. And what this is the terminator is inclined relative to, north-south. Yeah. And so the duration of hours we get within this campaign at different latitudes can be different. So if the terminator is inclined quite a lot, we might have very good coverage, let's say near the equator, and very poor coverage as we go further north. Whereas at more equinox conditions, the whole thing lights up at the same time, and we get full latitudinal range for the whole duration of the campaign. Hope that geometry of my hands makes some sense. So it could be that's playing into some of this. It's a good idea. I hadn't spent much time looking at it, but I should look at the duration of each campaign for each one of these. Basically, what's the longest possible period we could see for each of these? Because if we only have data for 4 or 5 hours, it's real hard to see wave periods beyond that.
Well, it sounds like during solstice, when the terminator is inclined, it's more favorable to see those smaller scale waves.
But it may be that just we can't see the long period waves at that time.
Okay. But on the other hand, during equinox, you're supposed to see both, right? But you didn't see like small.
It's
waves.
true. It's true.
Okay.
And I don't have an explanation, but it is a good thing to at least check that this is or is not a limitation of the number of hours each campaign ran for.
Okay. Well, yeah, I'm not an expert on that, but just curious about the distribution. But yeah, thanks for that. Okay. Other questions?
Yeah, I just on this figure. So is the spatial range or the wave range you can measure in the horizontal directions from about 100 kilometer to about 6,000? Is that the?
Yeah. I mean, that's going basically from down near a few. I don't think it's as small as 100, but down from a few pixels out to near the length of the as we approach the spatial scale of the slit. Now these are within this as well. is these wavelengths are not, this is not simply the wavelength along the slit, right? This is the wavelength after we've taken the component along the slit and the direction and the period to be able to get the true wavelength. Because if the wave's planar and it's propagating more perpendicular to the slit, then you see a very long wavelength along the slit, even if the true wave length is shorter.
Another question is on your comparison with the TIDs. You showed that almost a lack of correlation between the amplitude of the T-disk. Yes, that's right. Is this I mean, does this mean that you don't see much DTC when you see T-disk perturbations, or does it mean that when you see when you maybe see both, but it's just the amplitude of the TC perturbation does not really reflect the amplitude of the T-disk?
Yeah, it's the latter. So in this plot, I've only included the cases where we definitely see the same wave, right? So we see something moving at the same angular rate in both data sets. That only those ones are included in that panel. But it just says that when we're seeing them, they're moving at the same velocities, but we don't see a lot of correspondence in the amplitudes of the two signals.
Gone, please.
Yeah. Hi, Scott. Yeah, thanks for the interesting presentation. I just wondering why you would expect the TC would be correlating with others. So if I understand correctly, the measurements from gold O2 N2 is a column density, which mostly refracting anything below 200 kilometers.
Yep.
And the T-disk, I don't know, the temperature measurement is corresponding to what altitude?
They're basically the same.
Same.
Right.
So, but the TC, mostly in averaging above 200 kilometers.
So I don't necessarily expect them to agree.
Yeah. Okay. I'm just wondering. Yeah.
But it's worth plotting anyway, right?
Yeah. Okay.
No, you're right. Even if it was as simple as neutrals moving ions directly, I would need neutral observations at higher altitude. But on top of that, the ions, you can have a perturbation in the other hemisphere, can impact the ions. Perturbations down in the E region can impact the F region ions. So there's more going on with the TEC. Then there's also the direction of the wave relative to the magnetic field. There's many factors. So there's good reasons to not think these would be correlated.
Yeah, that's right.
But it's worth.
Right?
I mean, I have the data. I can plot a line.
That's true. Yeah. Thanks for the interesting talk.
I have a follow-up question. So, is there any other studies not using the gold, but other instruments, they like air glow or other studying gravity waves, and find there's a correlation with the DT, the amplitude perturbation? Or not, or similar result here, they're not correlated?
Yeah, I don't remember seeing a study that looked at lots of cases. I've seen some that look at single events and things, but I don't know the answer. I'm sorry.
There's a lack of statistical study of this kind of comparison, right?
Yeah, but specifically looking at the amplitude of what's seen in neutral perturbations and DTC, I don't know.
Okay, thank you. The reason I'm asking, because we are conducting a statistical study trying to compare like the DTC perturbation with the ultra low frequency wave perturbation from magnetometers and satellites. We do see a clear kind of well correlation. But yeah, it's a different kind of study, different kind of wave. So that's why I'm thinking about, yeah, for gravity wave, if there's such kind of studies.
Yeah. There may well be. I just don't. I don't know of one immediately.
Yeah, thank you. Yeah, very interesting.
Sounds like good motivation for modeling study, which we are working on.
It would definitely be definitely be something to you could look at with the models pretty readily.
Yeah, sure. Wenbin, please.
Hi, Scott. Thank you for the talk. So I have a quick question. You indicated even during quiet time in your last few slides, there might be gravity waves still or TADs certainly from the high latitudes. Do you have a sense how you separated either it's from high latitude or it's from lower altitude from atmosphere? Is any way to separate them out or something like that?
So for these cases here, and I didn't put all the panels in, but in every one of these days we see these are northern hemisphere campaigns, okay?
Mm-hmm.
And in every one of them we see waves moving southwards. They're mostly waves that we see from about as far north as we can see with gold,
Mm-hmm.
and coming down through the field of view. So they're coming from somewhere further north than we can see. And so that led me to see, well, is there some relationship to what's happening in the auroral zone? I don't have a I know there are studies that have looked at various indices of structure in the polar jet,
Mm-hmm.
other things down in the stratosphere, and compared those to gravity waves seen in the thermosphere. I haven't done that for this time period, but I can't prove there's a relationship here. It looks suggestive for sure.
Quick question. Oh,
Wenbin.
stop. Okay. A quick question, Scott. How often do you have this kind of campaign? Is that the purple? Is that how often? Every few days you have a campaign like this to measure gravity waves?
So that plot we were seeing there is this region here. I'm not sure if you can see my mouse, but it's that region where there's a thick green line in 2021. Most of these campaigns are very spread out. Many of them are done for a couple of days back to back because we would run the many of the campaigns, let me rephrase, have been done in conjunction with solar eclipses. I'm never using the data from an eclipse day because the eclipses make the detrending very difficult, and have a whole bunch of other complexities. But each time we have run one of these campaigns for a solar eclipse, we have run it for several days, including the day prior to the eclipse, so that we could get a baseline, so that we can test the commands for the spacecraft, things like that. And so that's why there's a strange spacing of the events, why some are north, some are south. Yeah, there are some limits on how often these can be run. During this time period, this is the sampling we've got. More recently, there has been more, including more in the southern hemisphere and such, but they're very infrequent and they're not evenly spaced. Many of them have been piggybacked on another opportunity. The set in July of 2021, the reason there were so many done at that time was there was a rocket campaign going on in Wallops, and we were trying to get gold data in support of the data these rockets would be collecting, sounding rockets. And so it was a Northern Hemisphere campaign. The slit lined up roughly with Wallops Island, and they ran several days because on each day they weren't sure when they were going to launch the rocket.
Thanks.
Okay, thank you, Scott. I think we are on top of 1 hour, and let's thank the speaker again. Okay, thank you everyone for joining, and I'll stop you. Let them know we are here in Boulder next time. I'd like to talk to you in person.
Thank you. Thanks, everyone.
Yeah.